In the previous sections, we looked at graphing logarithmic functions, and we're going to do the same thing in this video, except what we're going to do is we're going to graph the natural logarithmic function, and then also what we're going to do is we're going to take a look at transformations of our logarithmic functions. So, just as a reminder, the natural logarithmic function is ln of x, and it actually is a logarithmic function with base e, excuse me. So this would be y equals log e to the x is, or e of log base e of x is the same thing as the natural log of x. And if we wanted to write that into the exponential form, just like we would for any other graph, this would be e to the y is equal to x. And what we could do is we could just substitute these 5 values of y back in to be able to figure out what the natural logarithmic function looks like. So if I substitute 0 back in for y, that's easy. E to the 0 is equal to 1. Okay, so that makes it really nice and easy. And then for the other ones, we're just going to use a graphing calculator. Now remember, e to the first, we defined this a while ago in the very first section where we started doing exponential functions. E to the first is 2.7. All right, so that would be right here. And then what we could do is we could just go in our graphing calculator or scientific calculator, and we can get e squared, all right? And then we can get e to the first, which you already have. We can get e to the minus 1, and we can get e to the minus 2, all right? And so now what we have is we have 7.4, 0.4, and 0.1 for the other values, okay? So if we go, and so we've had 0.1, 0.4, and then 7.4. And we're just going to graph those values. All right, so we have our negative 2.1. Okay, so our x value is 0.1 negative 2, excuse me. So that's going to be right here. All right, and then we have negative 1.4, which is right about here. And then we have our good old stationary point, which is going to be 1 comma 0. Then we have 2.71, which is going to be right about here. And then finally, we have 7.4 comma 2, which is right about here, okay, approximately. And then we can go ahead and graph. This is going to follow the y-axis all the way down. And then we're just going to play connect the dots as best as we can, or as best as I can. And that's what our natural logarithmic function should look like. All right, now let's go ahead and see what the graph actually does look like in our graphing calculator. All right, so if we graph in the graphing calculator, we have y equals ln of x. All right, and remember we had a couple points just to verify this. We had 1 comma 0. We had the point as an estimate. We had the point. What do we have over here? We had 0.1 comma negative 2. Okay, so that fell on the graph about. All right, and then just one other point, just to be certain, we had what 2.7 comma 1, I believe. All right, and those aren't the exact values, but they are at least on the graph, so they look pretty good. Okay, so that's our natural logarithmic function. If we look at this, we know that the domain for this is going to be from 0 to infinity. All right, so domain 0 to infinity. And the range is going to be from negative infinity to positive infinity. And then finally, our asymptote is going to be x equals 0. All right, now, one thing to kind of consider is that, remember, the number e is approximately 2.7. All right, so another way we kind of think of an approximate sort of graph is if we had 2.7 to the y equals x, or 3 to the y equals x is a pretty comparable graph to natural log of x. All right, so this might be helpful if you ever kind of just don't have a calculator and you need to kind of get a quick and dirty idea of what the natural logarithmic function looks like. All right, so we're going to take a look at transformations as well as log functions. And you probably remember that we can shift up and down of a function. We could shift from the parent function just up and down by the number that's constant on the outside of the function. Whatever number's on the inside, we take the opposite, and that tells us which direction to move on the x-axis for a transformation. And then if we have a negative on the inside of the log, that reflects in the y-axis. If we have a negative on the outside of the log, that reflects in the x-axis, all right? So let's just take a look at a few of these sort of examples where we have f of x equals log base 2 of x, and we're just going to go ahead and graph each of these log functions that we're given by using rules of transformation, and we'll give the domain, range, and the equation of the asymptotes as well. Now, log 2 of x, just as a reminder, we did this in a previous video, but log 2 of x has this point, so we have the point 1, 0. We should probably have a few points on the function. And then we also had the point 2, 1 on the log function. All right, and then we just graph this, and it was still asymptotic to x equals 0. Okay, so this is our y equals log base 2 of x. One thing to kind of consider here, and we're going to go through this in the next section with a change of base formula, but if I ever wanted to graph this in a calculator, what I could do is I could use a change of base formula. And what I would do is I would just write this as y equals, I would say log of x over log 2. All right. In fact, let me graph that in the graphing calculator just to illustrate that that does work. All right, and that's a way that we can check these in our calculators. So log x divide log 2. And remember, we had a couple stationary points that we should be cognizant of. So we had 1, 0, and we had 2, 1 as points. Okay, so at least it makes sense that on our graph that those points exist. All right, and obviously we have our asymptote at x equals 0, just like almost every other parent function for logarithms. Now, let's go ahead and use this to kind of shift that graph around a little bit. So, and then we're going to check them with a calculator. So we have log base 2 of x plus 4. Now notice that the 4 is on the inside of the parentheses. And so if c is greater than 0, we're going to move c units to the left. So we're going to take that function, and we're just going to translate it 1, 2, 3, 4. Our asymptote is now going to be at x equals 4. Instead of the point 1, 0, we shift that 4 units to the left, and that's going to be negative 3, 0. And then we take the point 2, 1, and we shift that 4 units to the left, and that's going to be at the point negative 2, comma 1. All right. And so our graph would look something like this. All right. I know it's not that good, but just pretend it is. All right. And then let's go ahead and identify the domain for this. Okay, so for the transformation, that's going to be 4 left. So it's going to be 4 units to the left. For the domain, notice we start at negative 4, exclusive, and we go to infinity. For the range, that's going to be from negative infinity to infinity. And then finally, for the asymptote, x equals negative 4. In our calculator, if we want to graph this, we could graph this as log of x plus 4 divided by 2. Some points that we had, negative 3, 0. And then we also had negative 2, 1, right? And then the asymptote that we had was negative 4. And it certainly looks like that all the properties of this graph are reflexive of what we just did here, okay? So another example, log base 2 of x plus 2 minus 1. Transformations. So we have a plus 2 on the inside, so that means we are going to move left 2 units. We have a negative 1 on the outside, that means we're going to move down 1 unit. Okay, so our asymptote, instead of being at 0, is going to be at negative 2. Okay, so just imagine that goes through negative 2. All right. What we can also do is we could take those 2 stationary points. Okay, so remember we had this point 1, 0. We're going to move it 2 units left and 1 unit down. Right. And then we had another stationary point that was this point, which was 2, 1. We're going to move it 2 units left and then down 1 unit, which is actually going to be the origin. All right. And so if I graph it, it's going to look something like this. Okay. And those 2 points, the circles, those were the points on the original graph, not on the transformed graph. All right. If I look at our domain should be from negative 2 to infinity. Our range should be from negative infinity to infinity. And the asymptote is going to be at negative 2. All right. graphing this just to make sure that what we got made sense on our graphing calculator, we would just change this to x plus 2. And then we're going to have the minus 1 over here. All right. Points that we knew were on the graph were the origin, and we also had -1, comma, -1, I believe. All right, and that's another point that's on the graph. Asymptote was at x equals -2. All right, so this is what we should do just to verify that this graph makes sense to us, okay, as we're doing this. Reflections. So we have log base 2 of -x minus 3. So 2 transformations. So the first one is going to be that we move right 3, okay? And then we're also going to reflect in the y-axis, all right? So if we go up here, remember if the negative is on the inside, we reflect in the y-axis, okay? So that means down here we have right 3, and we're going to reflect our graph in the y-axis. Right? So here we go. So we are going to move this to the right 3 units, right? Which means that our stationary point, one of them was 1, 0, is now going to move 3 units, all right? And so here's our asymptote now, at least for the initial function, right? We still have to reflect this, okay? So we're going to take this point, and we're just going to move it 3 units to the right, and then we're going to take our other point, which was 2, 1, and we're going to move that 3 units to the right. All right, and this is what our original function would look like, okay? But what we're going to do is we're going to reflect it, okay? So checking in our graphing calculator really quickly, this will be -x minus 3, all right? And I want you to notice that now, and so if we were to have the original function, x minus 3, in fact, let me plot them both just to see the reflection, how that works, okay? All right. And then I'll also plot the 2 asymptotes. One of the original asymptotes was 3. The reflected is going to be -3. All right. So notice what happens is that the points. So we have one point which was 1, 0, or sorry, 4, 0. Well, now that point is reflected, and we have -4, 0. Okay. So what happens is our graph just moves over on the other side of the y-axis, which is x equals 0. Okay, so hopefully that makes sense to everybody when you guys are doing this, is that you're just taking this point and you're just moving it over. So if it moves 4 units to the right, it's going to move 4 units to the left for the reflected axis. Okay, so the actual graph, and all this over here, what I starred, that's just the for us to reflect. Okay, so when we get our final graph, we're going to move this, and our asymptote is actually going to be x equals -3. We have the point -4, 0. And then we also should have the point -5, 1. And our graph is going to look something like this. So the real graph should look like that about. All this other stuff is just helping us to get to that graph. All right, so let me erase this because this is all not going to be useful for us. All right. And the graph should, let me draw this line again for the x-axis, should look something like that. Okay. Obviously, in our graphing calculator, since we already did that, that would go away, that would go away, that would go away. And these are the points that we're left with. All right. So at least our graph makes sense. If we want to further verify -5, 1, that's another point on our graphed function. All right. The last one that we have is this negative log x plus 2. All right. So order of operations says we need to multiply before we add. All right. So what we're going to do is we are just going to reflect this first of all. Oh, and I'm sorry, before we go do that, we have to do domain, range, and all that stuff. So for the domain, that's going to be from -infinity up to the asymptote, which is -3. The range, still all real numbers. Okay, so -infinity to +infinity. And then finally, the asymptote is going to be x equals -3. All right. So going back to this problem, apologies. what we're doing is we're just taking the opposite of the log, okay? Then we're adding 2, all right? So when we do this problem, we're going to reflect and we're going to move 2, and we're going to reflect in the x-axis. All right, so let's get those 2 stationary points, and we're not moving anywhere left or right. So we know the asymptote is going to be x equals 0. Our stationary points are going to be this point here, and then 2, 1, right? But we're reflecting those, and then we're moving up 2, okay? So if we reflect these in the y-axis or in the x-axis, okay, so our transformations are going to be reflect in the x-axis, okay, and then maybe try to make that look like a real word instead of some weird Jones scribings. So reflect in the x-axis, and then we're also going to move up 2 units. All right, so if we flip all those points over, now this doesn't move anywhere, all right? So all we're going to do is just flip it over, and we're going to move up 2, all right? So what we end up with is just this point right here, all right? So we can get rid of that point. And then if we reflect this point over the x-axis, that's going to go down to, it's going to go basically down here, but then we're going to move it up 2 units, all right? And so what we end up with is just this point, okay, which actually is the original point, just so happens to be, all right? So, of course, and then when we flip it over, instead of it going increasing, it's more going to look like something like this, okay? And it's just going to continuously go down. But we can always check that with our graphing calculator, which we should do. Okay, so we're going to have the opposite of log of x and then plus 2. All right, so we just shift that up. All right, remember a couple of our points that we said were going to be on this. Okay, so if we look at this, our graph, so it looks like we should have the point 2, 1. All right, and it looks like it's right here. Let's verify that. So we should have the point 2 comma, or 1 comma 2, excuse me. All right, which we do. And then we should also have the point 2 comma 1, which we do. All right, so those are points that exist on the graph. The asymptote is going to still be at x equals 0 for us. All right. Another point that would be pretty easy for us to see would be 4, 0. That could be another point that we plotted earlier. All right, but again, we just reflected this over the x-axis. Okay, so and then moved it up 2 units. All right, so hopefully that helps out with the transformations and also how to be able to verify these by using our graphing calculators. All right, domain 0 to infinity, asymptote x equals 0, range negative infinity to infinity. All right, just to finish that out. All right, so we have one more topic in this section, and that's going to be able to find the domains of logarithmic functions just given the function itself, not given the graph.